Welcome to today's webinar brought to you by Couchbase, Cambridge Semantics, and Actian Corporation. I'm Stephen Fegg, Director at Database Trends and Applications in Unisphere Research. I will be your host for today's broadcast. Our presentation today is titled The Future of IoT, Real-Time Edge Computing, and 5G. Before we begin, I want to explain how you can be a part of this broadcast. There will be a question and answer session. If you have a question during the presentation, just type it into the question box provided and click on the Submit button. We'll try to get to as many questions as possible, but if your question has not been selected during the show, you will receive an email response. Plus, all viewers will be entered to win a $100 American Express gift card just for participating today. Now, to introduce our speakers for today, Priya Rajagopal, Principal Product Manager, Mobile and IoT at Couchbase. Sam Chance, Principal IoT Consultant at Cambridge Semantics. And Lewis Carr, Senior Director, Data Management Product Marketing at Actian Corporation. For more information on our speakers today, you can click on the arrows under their headshots. Now I'm going to pass the event over to Priya.
Thank you, Stephen. Thanks, everyone, for joining. So very quickly, a little bit of introduction about Couchbase. We build NoSQL database platforms for the cloud and edge. We were founded in 2011 and headquartered in Santa Clara in California here in the US, and we've got offices all over the world. Our solution is built on an open source foundation and combines the power and flexibility of NoSQL with the familiarity of SQL as a query language. And we count hundreds of household names as our customers. So moving along, how do we define the edge? The edge is really a spectrum, right? On one end of the spectrum, you've got standalone devices where the data is co-located with the applications that need it. Examples are smartphones, tablets, set-top boxes, etc. On the other end of the spectrum, you can have a number of applications, microservices, clients that share a database, and they're served by a data center that is in proximity of these clients. Think of this as an edge data center. So data is not necessarily co-located with the applications that consume it, but it is in close proximity. Examples are cruise ships, stores, factories, restaurants, etc. In both cases, the key takeaway is that the edge can operate autonomously with no connectivity to the cloud data center. So let's consider a typical cloud-only architecture. So you've got a number of clients consuming or pushing data to the cloud data center. Now, in an ideal world, where there is abundance of bandwidth and 100% reliable connectivity, all clients are up and running, applications are running, and they're serving their users. But we don't live in an ideal world, so any network disruption means that clients are down and are unable to serve their users. So this effectively translates to business downtime. So in contrast, let's consider an edge architecture. So you will introduce an edge layer, and we bring in data closer to the clients that need it. So as you can see in the figure here, you can have data in the pink boxes, represented in the pink boxes. They can be co-located with the client applications, or they can be in an intermediate tier as an edge gateway, where they could be aggregated and hosted. So consider an example of an IoT gateway, which is serving a number of downstream sensors and peripherals. So now in an online world, very similar to the cloud setup, all clients continue to operate when there is network connectivity. Now, of course, there's a major difference from the cloud architecture in that you have the benefit that the volume of data that's traversing the internet pipe is significantly reduced. And in addition, the latency in processing requests is also reduced because you are reducing the round-trip time costs that would take to hit the cloud to retrieve the data. So by bringing the data closer to the edge or to the clients that need it and processing it locally, you are making the apps more responsive. So let's assume the case where the internet connectivity goes down. As you can see in this model and on this architecture, the clients continue to operate. They can be served either by from the local database or from the edge data center. Now, if the connectivity to the edge network, let's say there's a disruption in the local network and the connectivity to the edge data center goes down, in such a case or such a scenario, the clients with embedded data, they would continue to operate. But of course, legacy clients which don't have the compute and local storage resources, they are going to be offline. So it's pretty clear that when we talk about edge architectures, it offers the benefits that it maximizes business uptime because you have guaranteed high availability of data, and so your applications and services continue to operate even under the conditions of low or no network connectivity. You get the bandwidth savings because you're reducing the volume of data that traverses the internet pipe. And of course, something which we didn't touch upon earlier is data privacy. It's a critical consideration for a number of applications. Several applications may disallow the transfer of data from the client to the cloud for any further analysis. So in such cases, local processing of the data within the application will alleviate such data privacy concerns. And finally, by reducing the round-trip time and avoiding that round-trip time to the cloud data center, we can have applications that are highly responsive. So sort of normalizing what we just described, we can come out with three options as far as cloud-to-edge architectures go. In the first option, the client is the edge and includes the embedded data store. Now you've got a guaranteed high availability all the way to the client tier. So even if the client loses connectivity to the cloud, it continues to operate. Now in the second option, we introduce an intermediate tier, and the edge moves to the intermediate tier where data processing is offloaded and data processing is handled on behalf of the downstream clients. So the intermediate tier serves a number of downstream clients which are not capable of local data processing. So note that although you don't get high availability at the client tier, you get the bandwidth savings and the latency benefits. And of course, the third option is the hybrid model where the edge can span between the intermediate tier and the cloud tier and the client tier. This, of course, offers the best of the first two models because you've got guaranteed high availability at the client tier, and you also have the bandwidth savings and the latency benefits and the data privacy concerns that we talked about earlier. So now, before we look at how Couchbase Mobile aligns with the cloud-to-edge models, a quick primer on Couchbase Mobile platform. So Couchbase Mobile is comprised of three components. It includes the Couchbase Server, which is a highly scalable, distributed, performant, NoSQL database platform. At the core of the database platform is our NoSQL document JSON store database engine. And it supports a number of services such as query, full text search, analytics, eventing, etc. So it makes for a comprehensive data platform. The key thing is that Couchbase Server can be hosted anywhere. It can be hosted in the cloud, or it can be hosted on-prem or on a private data center. Then on the far end, you've got Couchbase Lite. Couchbase Lite is, again, another full-fledged embedded NoSQL database platform. This is NoSQL JSON document store. It supports all the functionality that you would expect from a database, including query, full text search, eventing, analytics, etc. Now, the difference from Couchbase Server is that unlike Couchbase Server, which is a standalone database platform, Couchbase Lite is embedded within applications. So it runs within the context of your applications. Now, to get Couchbase Lite-enabled clients talking to Couchbase Server, we have the Sync Gateway. The Sync Gateway is the synchronization endpoint, which typically is co-located with Couchbase Server, and it's responsible for data synchronization between Couchbase Lite clients and the Couchbase Server. Now, Couchbase Server being a database, in a real-world production deployment, you are not going to, or it is definitely discouraged that you expose Couchbase Server or your database directly on the internet. So that's why you've got the Sync Gateway, which is the internet-facing component. Now, in addition to data synchronization, the Sync Gateway allows for enforcing access control policy, data authentication, user authentication, and authorization. And of course, everything is secured end-to-end with data encrypted at rest and in transit. And of course, you've got, as I mentioned, we've got access control policies which are enforced at the Sync Gateway layer. So I'll like to talk about how the cloud-to-edge architectures aligns with Couchbase Mobile, and I'd like to describe that in the context of key use cases. Now, consider a field application, right? You've got clients out in the field, consider oil rigs, construction sites, rural areas, disaster recovery areas, and such, where there is poor or virtually no network connection. But you want the clients to be able to function even in the face of no network connectivity. So in such disconnected environments, the clients will still need to have access to the data. So in that model, this architecture aligns best with that particular use case. Here, the clients have an embedded database and will be synchronizing with the cloud tier. So this is how Couchbase Mobile aligns. So in the cloud tier, you've got Couchbase Server. In the client tier, you can have Couchbase Lite as the embedded database within your application, and synchronizing data between Couchbase Lite and Couchbase Server would be the Sync Gateway. It's pretty straightforward. Now let's consider this use case where you could have a large number of hubs. Examples of hubs would be stores, factories, restaurants, etc. And each hub would have a number of clients and applications or microservices. Now, these clients could be legacy clients running on devices that are not capable of any local storage or compute. So, as an example, in a retail store, this could be applications running on legacy point-of-sale terminals. In this particular example, we are dealing with legacy clients which don't have local storage and compute resources. This architecture aligns well with that use case. And this is how Couchbase Mobile aligns in the cloud tier. As discussed in the previous use case, you've got Couchbase Server and Sync Gateway. In the client tier, you've got thin clients. There's no Couchbase Mobile here. There's no local data storage, no persistence layer. Now, when it comes to the intermediate tier, you've got a couple of choices. You can have Couchbase Server and Sync Gateway deployed as a small footprint right in the edge data center. As I mentioned, Couchbase Server can be deployed on-prem or in a cloud deployment, so you have flexibility in terms of where Couchbase Server is deployed. And of course, the Couchbase Server is going to be serving the thin clients that are downstream. But you've got another choice. In addition to having Couchbase Server as your edge data center, you could also have Couchbase Lite running within the context of a web services application. So this is a scenario where Couchbase Lite is embedded within your web server application, exposing a REST interface that could be consumed by the downstream thin clients. So the choice of whether you have Couchbase Lite or whether you have Couchbase Server as the intermediate tier really depends on the use case and the number of downstream clients. So if you're talking about a dozen or fewer clients, Couchbase Lite would work. But if you're talking about a large retail outlet where you've got potentially hundreds or maybe thousands of clients, think of a cruise ship where you've got 1,000 passengers. So in this particular case, you need a scalable solution such as Couchbase Server. So really depending on the volume of writes that are coming into the database, into the intermediate tier, you have a choice of Couchbase Lite in operating in a server mode or Couchbase Server as the intermediate tier. Finally, let's consider the use case where you would want the clients to switch between the cloud and the edge data center. So in this particular case, the clients could move with connect to the cloud data center, and when they are on-prem, they would connect to the edge data center. So the examples could be cruise ships. Consider the case of a cruise ship where you have users using their cruise ship app on their smartphones. Before their voyage, they could be making bookings and reservations and directly connected to the cloud data center. Now, while they are on the cruise ship, they would want to avail all the services available on the cruise ship, and they might connect to the cruise data center. And this is the most viable deployment model because the cruise ship could be offline for extended periods of time. There may not be a satellite connection between the cruise ship or the cloud data center. So in other words, while on the ship, the users would connect to the cloud data center, to the ship data center, and while they are on the shore, they would connect to the cloud data center. And in this kind of a use case, this model works well. And in terms of how Couchbase Mobile aligns, you've got in the cloud tier, you have Couchbase Server and the Sync Gateway. In the client tier, you've got your Couchbase Lite enabled clients. So in the example of the cruise ship app, you've got your cruise ship app with the embedded Couchbase Lite database running on the phones. So before when they are in the shore mode or before the voyage starts, the Couchbase Lite clients could directly connect to the Couchbase Server and Sync Gateway in the cloud. And of course, while they have an edge data center, the Couchbase Lite would connect to the Couchbase Server and Sync Gateway in the intermediate tier. So to summarize, edge strategy is the cornerstone of business-critical workflows, and Couchbase Mobile, with the flexibility that it offers in terms of deployment models, local storage support, and real-time data synchronization with resiliency to network disruptions, enables such cloud-to-edge applications. And I'll end on that note, and here are some resources for further reading. And over to you, Stephen.
Thank you very much, Priya. Now for our next speaker today, Sam Chance, Principal Consultant IoT at Cambridge Semantics.
Okay, thank you, Stephen. Today, our focus is on the role of semantics and graph data model in IoT, especially at global scale. By way of introduction, Cambridge Semantics helps organizations make their enterprise data easy to find, understand, and use so that they can use data and analytics more effectively and frequently to drive the business. We are experts at using the graph data model and semantics to expose business meaning and connections between data points across vast landscapes of previously siloed and complex data, including unstructured content. We're based in Boston, and we were founded in 2007 by a team of semantic experts from IBM. Their initial focus was on developing a framework of tools that allowed companies to apply enterprise semantics to apply semantics to enterprise data. Our product, Anzo, was first released in 2009, and we released a massively scalable version of Anzo in 2017. Anzo is used by companies in pharma, finance, material science, healthcare, and government. Okay. Current trends such as IoT, smart manufacturing, Industry 4.0, connected enterprise, digital twin, and digital thread capture the imagination and promise to achieve unprecedented levels of automation and autonomy. For our purposes, we summarize all these initiatives under the umbrella of digital transformation. But two critical aspects of the depicted ecosystem are complexity and heterogeneity. There are myriad data and message protocols and formats, and there are many actors with many goals. For example, in a supply chain ecosystem, there are suppliers and consumers. Sometimes they cooperate and sometimes they compete. But to achieve an adaptable and highly connected ecosystem, network of ecosystems, and indeed world, it is imperative for information systems, devices, and the like to interoperate and expect change, not simply cope with it. Let's see. It turns out that the graph data model excels at managing complexity, heterogeneity, and anticipating change. And machine understandable semantics, as we'll see later, are superior for creating shared understanding at the machine level and for enabling large-scale machine-to-machine autonomy. So with that said, our first assertion is that graph and semantics are key enablers to digital transformation at global scale. So we say it's about interoperability. And in this context, interoperability is for nodes and systems, especially automated processes to exchange and understand exchange information without knowledge of the characteristics of the inner working of collaborating entities. And this has to happen at global scope and scale. To repeat, interoperability, especially data interoperability, is a key enabler to digital transformation and to achieve the envisioned autonomy and automation. In other words, digital transformation requires data interoperability. In fact, without interoperability, organizations will continue to apply disproportionate time and resources on costly and inefficient data searching, preparation, and organization activities. The nature of operations remains a manually intensive endeavor, and the desired large-scale autonomy eludes us. In the next few slides, I'll briefly discuss unregulated or point-to-point, standards-based, semantic, and sustained levels of interoperability. Unregulated interoperability, believe it or not, is the most common. Sure, there are many standards and platforms, yours, mine, and theirs, but true global interoperability is largely unregulated. At this level, each message exchanged between two different participants requires an initial effort to implement a mediation or a mapping between the two models used by each participant in the network. As seen in this graphic, a common example is that the same concepts can be represented in many ways. And to be sure, this is just one pattern. And each time a new participant joins the network, it causes a substantial increase in the total number of mediations within the network. That is to say, there are mediations for each link. This results in a combinatorial explosion in the number of mediations as the network grows. Adding one new node ripples changes throughout the network, causing substantial rework to return to relative harmony. This is obviously a filter to interoperability and is an inefficient means to share information and create a shared understanding. Standards-based interoperability is characterized by dedicated and shared reference models. Reference models and other standards are developed to enable organizations to exchange information based on a shared understanding. When a new participant joins the network, only one mediation is required to communicate with other participants. The number of mediations ends up being more linear with the number of participants in the network. In practice, standards-based interoperability manages message and data formats and structures. However, clarifications remain required for semantic issues, especially for unambiguous machine-to-machine communications. Semantic interoperability is the ability for computer systems to exchange data with unambiguous shared meaning. Semantic interoperability is a requirement to enable machine, computable logic, inferencing, knowledge discovery, and data federation among information systems, especially at scale. Without machine understandable semantics, and despite standards for formats and structures, information may not be unambiguously understood by others, especially machines. Semantic interoperability adds machine understandable context and knowledge enrichment to address these issues. Okay. Sustained interoperability maintains network harmony. This is actually an area of research that involves complex adaptive systems theory. Organizations and networks must adapt to survive. Change is constant. Models change, semantics change, and this results in breaking down the harmony of the network. For example, when one member adapts to a new requirement, it creates a ripple that propagates through the network, and the network begins experiencing interoperability problems. One model for sustaining interoperability includes a monitoring system that detects actions that break network harmony. Upon discovery of a change, an intelligence integration layer interprets the change and devises a mitigation strategy. Then a decision support system assesses the strategy and decides on a course of action, and then uses the communications layer to notify the network of the corrective action to restore network harmony, and the network restabilizes. The knowledge base there in the center provides the unambiguous machine understandable information, which serves as a substrate for increasingly autonomous machine-to-machine interactions. Point-to-point versus the semantic model. For those familiar with the early days of service-oriented architecture, this slide represents a similar dynamic that was in play during that period. Service-oriented architecture sought to improve upon point-to-point design. Part of the challenge then and now is that immediate gratification that comes from focusing inwardly. This arguably starts at the project level. Engineers and managers prioritize the project over the larger ecosystem or even the community. If you think about it, the internet and the web are miracles in the sense that they are both about community versus local needs. But focusing inward increases brittleness that stems from point-to-point mediations as projects begin interacting with external systems. If we can agree that information flow through an information system is a key metric for value, we can conclude that constant mediation activities, namely data preparation processes, result in great cost for enterprises with only modest value added. Our second assertion is that organizations should invest in the semantic model early at the project level. This has the effect of increasing connectedness and information flow, which, by our metric, yield greater value at a fraction of the cost as the project begins interacting with other systems or communities. This approach benefits the enterprise, the ecosystem, and ultimately the global landscape. So focusing at the project or enterprise level, let's consider how this works. The contemporary data management architecture ingests, catalogs, and normalizes enterprise data assets into a graph. Using semantic standards, the normalized graph is considered seamless and self-describing. These characteristics virtually eliminate structural heterogeneity. Next, the normalized data is described and harmonized using semantics, more specifically ontology models. Semantics describe and organize otherwise disparate information and provide a business-oriented view of concepts and relationships within and among the contributing data sources. This is often called a semantic layer. And with a semantic layer in place, automated and human clients can further blend and partition data into application or analytic-specific subsets. Notably, the subsets may be easily linked or federated as required because all content is normalized and harmonized into a semantically described graph model that is designed for connecting. The net effect is the realization of a unified information access layer optimized for human and machine consumption. The project, the enterprise, and the ecosystem, and ultimately the globe shift toward higher order interaction patterns such as conversations, increased delegation to automated processes, and more self-organizing behaviors. This graphic depicts a conceptual view of the semantic layer, or sometimes called a knowledge graph. Functionally, this layer provides data discovery and access to highly connected and contextualized content. In other words, disparate data is linked, semantically described, and uniformly accessible. Imagine the consequences at global or ecosystem scope and scale. From a product point of view, ANZO is a lightweight overlay on existing enterprise data management landscape. ANZO works seamlessly with legacy and contemporary investments and provides a modern way to empower business users and reduce reliance on IT. In fact, creating a semantic layer inverts, if you will, the application development process. What I mean is that instead of waiting for IT to wire together data for each application or set of known questions, the semantic layer allows human users and perhaps more significantly automated processes to ask virtually any question of the data fabric. We say colloquially, users ask questions tomorrow they didn't know they had today. In other words, semantic interoperability provides unprecedented flexibility, adaptability, and autonomy. And without regard to where the data is, how it's structured, or where your computation is. This is another product detail, but ANZO works out of the box with leading desktop analytic, BI, and data visualization tools, so your end users continue to use the tools that they know and that they love. So this brings us to our third assertion, which is semantic technologies need not be disruptive to data management investments or data access investments. Finally, our last assertion is that the killer application for the graph data model is large-scale data integration. Graph analytics are, of course, valuable and important, but global data interoperability will unleash inestimable autonomy. Okay, that concludes my portion. Thank you so much for your participation and attention. I hand it over back to Stephen.
Thank you very much, Sam. And now we're on to our final speaker today, Louis Carr, Senior Director of Data Management Product Marketing at Actian Corporation.
Thank you, Stephen. And I want to say good morning, good afternoon, and good evening to all of you that have joined live or who are going to be listening later when this is on demand. As Stephen said, my name is Louis Carr. I'm the third speaker, and I'm going to try to pull through a few points here and there that both Priya and Sam made, but largely the key topic I want to discuss here you see on the screen, which is let's really look at the relationship between analytics and data management and how, because of the changes in the resourcing at the edge, you're going to see changes in the amount of data, the analytics applied to it, and therefore a need to change the type of data management that we do going forward. Now, a little bit about our company, my company, Actian. We are 100 million plus in revenue. We're growing at double-digit percentage. We've been around for quite some time, not with the name of Actian necessarily, which is why some of you may not have heard of us. But if you've ever heard of Ingress or Pervasive or Btrieve or Vector or Matrix or Data Junction, the list goes on. There's a lot of data management, integration, and analytics products that have real innovation over the decades that have been subsumed into our company. Although we're independent and about 350 employees across the globe, we actually are backed by 80% ownership by a $10 billion company called HCL. So that gives us some latitude to invest and further our innovation. So, what I'd like to talk about, again, is the edge and analytics. There are just a multitude of use cases that fit into this. Sam mentioned digital twinning. There are many others that Priya mentioned as she talked about the different architectures that Couchbase can bring to bear, on handling the data management with all of these use cases. So I'm going to not say much about this because I think everything that's been said about it is just fine. The thing that I'd like to put a little more emphasis on is just to stress that underlying all of those use cases, all those scenarios that have been mentioned, whether you're looking at them from the cloud or the data center, holistically across all of the different data sets and trying to take a semantic approach to managing and manipulating that data as Sam described, or you're talking about, hopefully trying to, as Priya said, look at the data from the cloud moving back down into needing, because of latency reasons, manipulation at the edge. All of this is happening because there are simply more resources available at the edge, and those resources are going to generate data that will need analytics local. And the type of analytics that will be applied, I believe, will begin to be common building blocks. So take machine vision, for example. Maybe it's applied differently for facial recognition than, let's say, looking for, hairline fractures in ceramics on assembly line. But the point is that those core algorithms, and therefore the code, and therefore the libraries to build up that function, they can be a common denominator. They can be reused. When I was an engineer, I'd leverage libraries that came from various instrumentation companies or routines for drivers to do, let's say, analog digital conversion, which is, you see the analog to digital signal processing. And I would also have common routines to apply to those, even though I would, was doing different analog signal input. I'd have to do temporal noise filtering, so the signal noise filtering, and I'd reuse things. Well, that's what you're going to see happen over time. And the point at which this is done will change. I remember as an engineer, at first, back in the 80s, we didn't have the compute horsepower for me to necessarily, when I collected all of these different analog signals, to do the processing out at the edge in the field. But over time, by the 90s, a lot of what was sitting in a mini computer was available for me to put into a server and then later into clients and move them directly out to that edge so I could do a lot of the processing at the edge versus waiting to get back to my laboratory to do that processing there. And that's the thing, is that all this data is not necessarily, I want to reduce what's going from the cloud out to the edge. It's the reverse. I'm trying to reduce how much data I send from the edge back up into the cloud. Now, that's not to say that some of this data won't need to be sent back up, or the data won't need to be extracted from the cloud, largely for contextual or guidance purposes as to what analytics to perform or what guidance to give, either to do an execution by a machine or to provide a decision advice for the actual end user. So the point is that the edge is fairly fluid. I think Priya did a great job of describing, what is going to be out at the edge, right? But I think it's important to understand from a data management standpoint that you're going to have to look at how you bucketize that edge and then look at within each of those buckets, what are the resources? What's the type of edge data management that's going to be required? Now, one thing that I differ a bit about is that, regardless of whether you're going to use a database, because at some point, the resourcing just won't be there to use a database as your data management approach. But there will almost always, invariably, as we go forward, unless you're going to the very extreme of an 8-bit microcontroller, virtually everything's going to require some level of persistent data, even if it's just something applied at low power. And increasingly, even at low power with something like a 32-bit microcontroller that might be sitting in a very far-in edge device, you're still going to see analytics applied, even things as sophisticated as machine learning. So if you get a chance to look at something like TinyML, you'll see exactly what we're talking about there, where there is this opportunity for much more in the way of data being done through an analytics machine learning approach. So if you look at each of these, I've tried to give examples. It's such an eye chart, I'm not going to try to go through it all right now, but let's just take it in layers. At each of these layers, for each of these areas, probably from the 32-bit microcontroller all the way up to the cloud, you're going to have different requirements on what's necessary for the data management system and different constraints on within that platform what you'll be able to apply. And you can see some of the examples of the types of systems that you could expect to be innovated and built based on that set of resources. So at the mid-range here for the edge device in the third column, that's where you start getting into very sophisticated machine learning, deep learning, neural networks beginning to really take hold in a unsupervised fashion where gigabytes, if not up to a terabyte of data in many cases, are going to be manipulated and analyzed locally, and decisions will be made there at that device, which means that by the time you get to the edge gateway, as Priya said, it's really the new manifestation of what was at one time in a data center. And so at that point, then you're not just talking about, oh, I removed latency, but I'm also talking there about, okay, at that point I need concurrency. I need to be able to publish and subscribe back and forth between that grid of edge devices, which in turn have a larger grid of smaller devices sitting out there in that first column, which I'm calling a IoT grid or Sentinel set of devices. So the latency issue isn't just an issue of latency between the edge and the cloud. The latency issue and the concurrency issues combine to be an issue as to why more and more of that point of action will move further and further towards the left. And as you can see in these green arrows, these are the things that will drive it. So with all of that, you have to then ask, well, what are going to be the requirements for data management out at the edge? And for us, we believe there's really 8 major things. Now, one of the key ones here to understand is that as long as I need persistent data and I have analytics running that are being applied to that persistent data, I'm going to need to move from whatever I'm doing now to increasingly a more robust standalone database on each of those devices. And because this is a fractured environment, yes, there is some consolidation, but it's still fractured. I need to make sure that database can run on any platform and that it can be either standalone as a database or it can be embedded directly into the application. What I mean by that is that the actual database engine would need to be rolled into the application. The types of data that we see aren't just going to be JSON. They're not going to simply be the traditional structured data coming from, let's say, pressure, volume, temperature. You're going to be looking at sometimes streams of images that are unstructured, but having said that, there's metadata that is structured with them. So the large binary objects will be an issue. You're going to basically have a client-server environment all the way out to the edge. And you're going to have to deal with this in a very stateful and stateless way. This will all be with high speed, but you want it to be on a platform where you can do the visualization. So with our particular set of software, and I neglected to mention, we do all sorts of data management systems. We have graph NoSQL databases. We have hybrid cloud data warehouses, Avalanche being the most prominent of those for us. But we also have an edge data management platform called Zen. And Zen is basically able to do both SQL and NoSQL access. It's able to interact with databases, repositories, applications that might reside both locally, a tier up, or back in the cloud, or even back in the data center. The key for us, though, is that we want to make sure that there is no need to do any sort of transformation of data between these tiers. And the reason for that is that anytime you do a transformation, you get a performance hit, you create a security vulnerability. So for us, we built this as a modular platform where for the smallest client that I would embed directly into an application, that engine plus all of the capabilities to do ACID compliant SQL, CRUD with NoSQL, all of that's into a 2 megabyte dynamic link library or a .so or whatever package goes with each of these development environments and OS environments. Even for the server version, we can move that all the way out into a device because the maximum footprint for that, or the minimum footprint for that, is 30 megabytes. Our maximum is under 200 megabytes, even for our full enterprise version of this. So what does that mean to say I don't have the transformation in the ETL? Obviously, I still have extraction, right? I'm going to query that data, or I'm going to do a time series set of data, and we have all the functionality to do time series. But I want to be able to move it around without doing any transformations to it. If I have to move it around where I've got multiple databases, invariably I have transformations. If I have SQLite going to Postgres or MySQL or Microsoft SQL, whatever it may be, I have to do transformations. Well, what if you had a single modular database that you could move to be pared down to the types of resources it needs to fit into? I can remove all of the ETL. I can remove all the vulnerability. I can improve the performance. We have benchmarks to show how that happens. And I get a single solution with a single database. Now, what does this mean for your team? Let's just put it, the two key points I want to make there, and running out of time, but essentially what you would want to do is ensure that all of your developers, your data scientists, or they can develop in any language they want. They can use NoSQL, they can use SQL, doesn't matter. They can use either one, right? They also can work with their business partners. Let's say there's line of business that are doing queries. They understand how to use SQL and they want to remotely query, or you want to remotely pull data in as a data scientist so that you can create a model or train it or tune it. Then having a single database that will go all the way from the cloud all the way down into the device with all the same API calls or just standard SQL query means that you're not fighting over a point of friction of which platform should I choose, or settling for sprawl because nobody wins and you end up with a lot of different platforms. And the other reason is that, again, these building blocks for AI are going to begin to move around. Where you do the processing is going to move around. And you want to have that flexibility to support that, particularly over time as the hardware changes and improves and the software libraries change and improve. So if you want to know more about this, there will be links in the presentation where you can look and look at this in more detail. So with that, I want to thank you for your time and thank Pri and Sam for being part of this with me as well. And I'm going to turn it back over to Steve.
Thank you very much, Louis. And at this point in time, we're going to dive into questions from our viewers today. The first question is for Priya. Priya, you mentioned sync protocol in context with Couchbase Mobile. Can you briefly describe what it does?
Sure. We have a synchronization that is supported between Couchbase Lite-enabled clients and Sync Gateway. And of course between Couchbase server clusters, so that would be relevant in the context where we've got an edge data center communicating with a cloud data center. So specifically in terms of the synchronization protocol, it is scalable and highly resilient to network disconnects. So it has a retry logic built in with exponential backup, so you can detect if there's any changes to the status of the network connectivity and resume connection. And if you've got hundreds of thousands of connected clients synchronizing with a data center, the synchronization protocol has a checkpoint mechanism to ensure that even if clients are disconnected for a period of time, when they resume connectivity, that the synchronization picks up from the last synchronized checkpoint. So a lot of flexibility in terms of directionality. You can push data, you can pull data unidirectional, or you can have fully duplex communication over push and pull. So, and of course, filtering mechanisms are in place to ensure that only a relevant subset of data gets synchronized over to the clients or gets pushed from the edge over to the cloud.
Can I follow on to answer that question as well, Stephen?
Oh, sure. Absolutely.
Oh, okay. So with us, we don't have a sync server. That does not mean that many of the functions in that sync server aren't absolutely necessary. We just have them distributed differently in our architecture, largely because we have the exact same architecture for that small embedded engine that would be equivalent to the Couchbase Lite product. We also have a very small version. Our footprint for even what would be their Couchbase server is under 200 megabytes. So you literally, and it will do up to 1,000 concurrent clients on any one instance. So essentially what we see again is this whole idea of what was in the data center being decentralized and moved further to the edge of the network, where it may literally sit on an IoT gateway, for example. So as a result, this just as Couchbase has the flexibility, we do as well. We also think a lot of the things are going to be application dependent. Things that aren't application dependent that you'd want built in, like auto reconnect if you've lost connectivity, the ability to sync up the data sets, using the same file format underlying so that we don't have to decrypt as we move the data from one side to another. It's worth looking at all of the architectures out there, because what you do may be very specific and need a different architecture for a different project.
Understood. Thank you, Louis. Sam, our next question is for you. What standards are applicable to semantic interoperability?
Great question. So there's an important distinction between ontology and, say, formal ontology. And I argue the key standards to study and learn about, and these are the ones that were, based on our World Wide Web Consortium, or W3C, Web Ontology Language, or OWL, OWL, Resource Description Framework, or RDF, and Sparkle, which is the protocol and RDF query language. So those three standards would be the key.
Understood. Thanks, Sam. We just got a new question in from a viewer, and I think it's one that I'd be interested in hearing all three of you weigh in on. And why don't we start with you, Priya? Is the assertion from the speakers today that more and more data needs to be dealt with at the edge as opposed to the recent move to the cloud?
Okay, I can take a first stab at it. I think edge computing complements cloud computing. It's not the either or. What I think, at least from what I'm asserting from my part of the presentation, is that having an edge strategy is important if you are dealing with business critical application where any sort of downtime is unacceptable, where bandwidth, latency considerations, data privacy considerations are important, then processing data closer to the edge is important. And that's really the only way you can guarantee the responsiveness and the high availability. But of course, at the end of the day, when you're talking about massive volumes of data that needs to be aggregated across all the edges, and you need to have an analytical view of the data that can affect not just one edge, but spans multiple edges, you need to have something like a cloud, right? An example would be a recommendation engine, right? On the edge, you do have ML running on your phone, and you can do some personalization right there locally on your phone itself on the edge. But then if you're trying to implement a recommendation engine there, you're probably going to be doing something like a content-based filtering, right, where you have a local view of the data. But then if you're doing something like that on a cloud scale, where you've got an aggregate view from not just that one user, but then from hundreds of other users, then you can do something like a collaborative filtering. So it really depends on the use cases, but really the assertion is that bringing the data closer to the edge is going to be important and has to be part of your strategy, but definitely complements cloud, and cloud is definitely here to stay and has a lot of benefits, the reason why it was deployed in the first place.
Got it. Louis, your thoughts on the question?
So I thought Priya's answer was superb, and I agree wholeheartedly with it. The only thing I would add to it is that the edge is just generating so much more data, and with the advent of 5G and the higher bandwidth, not to mention you have bandwidth increases not just for smartphones and video surveillance cameras, et cetera, which will leverage 5G, but you've got this whole IoT grid out there of all sorts of sensors that are going to begin to leverage things like tiny ML that will run on low power and leverage the increase in bandwidth from Cat-M, which is basically a 4G LTE environment. There is absolutely no way with this deluge of data that will be generated at the edge to move even a fraction of it up into the cloud, given the latency issues. Yes, 5G is faster, but you're just going to get overwhelmed by that amount of data. So by application in each of the industries, taking into account what Priya said, you're going to have to look for the analytics being run unsupervised, with the data management needing to run unsupervised as well in support of it locally.
Understood. Thanks, Louis. And Sam, any additional thoughts on the question?
Sure. I first of all, I thought those were great replies. I think part of this is a dilemma, and the dilemma is, on the one hand, the data is created and going to increasingly be created by and on the edge. On the other hand, my whole thing was about semantics, right? So I'm talking about integrating and contextualizing disparate data. So part of the challenge is to do as much as you can on the edge in terms of analysis and processing, but I would say the sooner you can contextualize the information, the more processing power and autonomy that you'll realize. So how can you do that with, like Louis was saying, you can't just send all that data to the cloud. So if you agree to some degree of semantics, orders of magnitude less, that can be the logic glue that links the data together, but then you can process that data at the edge in as much as practicable. So the data can be anywhere, but the semantics are the part that will provide that logical global cohesion. So as soon as you can, on the edge, represent the data that you generate in alignment with the ontology or ontologies that allow for the unambiguous machine understandable data. So globally, use the semantic metadata, locally generated your data aligned with those semantics is something I would urge you to consider.
Thank you, Sam. That is all the time we have for questions today. We apologize that we were unable to get to all of your questions, but as I stated earlier, all questions will be answered via email. I'd like to thank our speakers today, Priya Rajagopal, Principal Product Manager, Mobile and IoT at Couchbase, Sam Chance, Principal Consultant, IoT at Cambridge Semantics, and Louis Carr, Senior Director of Data Management Product Marketing at Actian Corporation. If you would like to review this presentation or send it to a colleague, please use the same URL that you used for today's live event. It will be archived, and you'll receive an email as soon as the archive is posted. And just for participating in today's event, you could win this $100 American Express gift card. The winner will be announced on March 31st. We will reach out to you via email if you are the lucky viewer. Thank you, everyone, for joining us today, and we hope to see you again soon.
Thank you, ladies and gentlemen. This concludes today's webcast. We appreciate your participation. You may now disconnect. Presenters, please stand by.